All right, guys, this is the first lecture for MGF1100. Should correspond to homework one. Just a couple things before we get going. We are doing this through Zoom, or I'm doing this through Zoom Capture. It is not live. Obviously, you're watching it on YouTube now. Feel free to stop the video at any time if things go too quickly. The fidelity from this dock camera, the resolution has been surprisingly bad. I'm not real happy with the quality of the video this is taking. This may be the only option at the moment, but hopefully in the future we can get these to look a little sharper. But for now, I'm kind of using thicker marker to compensate for it. So hopefully that will improve as we go. So like I said, feel free to pause. If you have any questions, send me an email. The first homework is pretty straightforward and mostly just vocab. So what we're going to be talking about with homework one is the number sets. And give me feedback on the video. If you're having trouble reading these, don't watch it on your phone. I think the fidelity is going to be so bad that's not going to be possible. Try watching it on a laptop at least for the video. The audio will work, should work anywhere, but the video, it's going to look probably pretty poor on a phone. But if you can't read this or, whatever, just give me some feedback and I'll adjust as best I can. So the number sets, basically what we're talking about here is vocabulary. So when I talk later in the course about integers and things like that, you need to know what I mean. So the first set we're concerned with, and this is the smallest set, and we'll draw a diagram later, is the natural numbers. The natural numbers you can think about as just counting on your finger numbers, 1, 2, 3, and so forth, up to 100, keeps going right out to infinity. Make a couple notes about the natural numbers. They're all positive. There is no zero, no fractions, or decimals, right? You don't want to necessarily try to remember it's about every single set. These are the natural numbers and they're positive, no zero, no fraction, you know what I mean? But just make note of that. These are just the positive numbers. There's nothing in between them. We're not worried about 1.5, 2.5, 2 2/3, anything like that. Just, whole, clean, positive, well, I shouldn't say whole numbers, but clean, positive, solid numbers, okay? The next set, the next largest set, because we are building up from smallest to largest, is the whole numbers. The good news with the whole numbers is there's not a tremendous amount of difference with them. And the natural numbers, the difference mainly is that we are adding 0. So 1, 2, 3, and again, all the way out to infinity. And the same things still apply here. It's positive. This time there is a 0, right? So that's only true for the natural numbers. There is a 0 in the whole numbers, but still no fractions or decimals. So again, don't get too caught up on memorizing the facts here. I'm not going to ask you to list out all the facts of the natural numbers and whole numbers. I'll simply expect you to know what I mean if a problem might have 2 answers, let's say, and I would say, select the integer answer. You need to know what I mean, okay? So this is mostly a case of vocab, not so much a case of, memorizing little tiny details. Just understand, the natural numbers are your counting numbers, and the whole numbers are your counting numbers plus 0, all right? The next set, and probably the first one that you may not be familiar with, are the integers. The integers are where the negatives come in, okay? So we had the whole numbers, 0, 1, 2, 3, and so forth out to infinity. Remember, that's the whole numbers right there. Just that bit there is the whole numbers. Keep that in mind. What we're going to do is take those whole numbers, add to them, and take all the negatives of those whole numbers. And now we have those as well, okay? So again, 0, 1, 2, 3, no fractions, no decimals. We still haven't talked about that. We're just taking what we had a minute ago with the whole numbers, 0, 1, 2, 3, etc., out to infinity. And now we're going the other way, 0, -1, -2, -3, out to negative infinity. I notice it's a little crooked on the screen. It's straight to me, guys, so I'm not really sure what the deal is. I'll do the best I can. Just again, we're all in new territory here with this online thing, so we'll do the best we can. And again, I'll recap here in a minute with sort of a visual diagram. Right now, we're just sort of writing out the definition. So the important thing about the integers is this is where you get signs. We already had positive numbers, but now we have positive and negative numbers. Signs, again, you already had positives, but when we say signs, we mean positive and negative. That's where the integers come in. What's important, because this is where people start getting confused, there are still, let me bring that up a little bit, there are still no fractions and there are still no decimals in the integers, okay? So just to recap, the natural numbers, 1, 2, 3, 4, just your counting numbers, your caveman numbers, right? They didn't have fractions back then. They didn't have decimals back then. Then we moved into the whole numbers, added in 0. That was about it. The integers, we took our whole numbers and added in the negative whole numbers, but still, again, no fractions, no decimals, okay? So take a minute, familiarize yourself with these. and then we will get to the next one. The next one is unfortunately where it gets a little bit tricky. The next one is the rational numbers. So let me list out what we've talked about already, not the whole thing again, but just, you know, a brief. Natural, then we had whole, then we had integers. Now we're moving into rational numbers. So one more time, remember the integers, the natural numbers are just your counting numbers. The whole numbers introduces 0. If you want to think about like that's kind of its key point. And the integers introduce signs. Again, you did have positive already, but now with the integers, you have negatives as well. So the rational numbers. Rational numbers are where we do introduce most, and that is the key word here, most fractions and most decimals. Do not make the mistake to say rational numbers are where all the fractions and decimals come in. That is not the case, okay? There's no easy way to write out the rational numbers in a line either, because if I say 0 and then 1, well, what about all the numbers between 0 and 1? Well, most of them are included. Most of the fractions, most of the decimals, those are rational, but not all of them. And it's impossible to sit there on a number line and say, well, this number's not in there and that number's not in there, when there's millions and millions of infinitely many numbers, right? So unfortunately, the rational numbers is where this gets a little sticky. So I'm going to go ahead and show you the definition for the rational numbers. It's a little confusing. We will walk through it. And again, this is in the textbook too. The videos, I mean, frankly, guys, they're optional. I would assume you'd want them because that's part of what you paid for. But if you are comfortable with learning straight from the book or the learning aids through the homework, that is certainly your prerogative. These videos are here strictly to help you. So again, let me know if I can improve them in any way, reasonable way. So the rational numbers, this is the definition. P over Q, where P and Q are integers. Take a minute, write that down, and more importantly, think about what that means. It may not even be super obvious to you at the moment. P and Q, where P and Q, P over Q, excuse me, where P and Q are integers, right? Everything was fine up until now. Now all of a sudden we've got this ugly, ugly definition. So obviously the rational numbers are the issue here. This is the one you're gonna want to spend the most time on. First of all, what are P and Q? They're just variables. Could be X and Y, okay? If you want to put A and B, you can. The reason they use P and Q, presumably, is because P and Q follow R, right? Well, they're related around R, element, OP, QR, you know what I mean? P and Q are simply the variables chosen to represent a rational number. They could be literally any variables you want. So if for whatever reason the P and Q are throwing you off, call it A and B, all right? So think about what this looks like. What I basically said here is this is what a rational number should look like. Well, that's a fraction, isn't it? We're not into fractions yet. We have a whole chapter on fractions. We'll get into that at some point, but we're not there yet. Right now, I just want you to recognize that P over Q, that is a fraction. So what rational numbers are is they're fractions, with this exception here, where the P and the Q are integers. What does that mean? Well, basically what we're saying here is you can make a fraction. If you can make it a fraction, it's rational. But think about it. Let's just pretend for a second that I covered up the other part of that definition, right? And I just said rationals are P over Q. That's it. Wouldn't that be every single number ever? Couldn't you just say, well, here's the number 3, and I wrote it as 3 over 1, so that's rational. And here's the number -10, and I put it over 1, so that's rational. And here's 2/3, and that's rational, right? Because they're all fractions. They're all P over Q. And if you may not know how to do this yet, but decimals can be converted into fractions, right? Oops, I just wrote the decimal again. 1 1/4, right? And then we have a fraction again. So the point is you can write everything as a fraction by putting it under 1. That's where this extra bit here comes in, okay? So this is important. P over Q, where P and Q are integers. P over Q, meaning it's a fraction, but the fraction itself has to be made up of integers. So let's go through some examples and think about what I'm saying here. Take the number 7. Is it rational? Well, yeah, because I can write it as 7 over 1, which does match the fraction format. Hopefully you agree. And think about this as the qualifier. P and Q, 7 and 1, are they integers? That's the key question here. Are 7 and 1, the numbers that you made to write this as a fraction, are those integers? Yes, they are, because what's an integer? Any positive or negative whole number. So 7 is rational. What if I took the number 4/5, 4 over 5? Is that rational? Well, it's P over Q, isn't it? So it's a fraction already, so that's good. And are the numbers P and Q, 4 and 5, are they integers? Well, again, an integer is any positive or negative whole number. 4 is a positive whole number. 5 is a positive whole number, positive or negative. So yeah, 4/5 is rational. Basically, normal fractions will be rational, right? We're not, getting a little ahead of ourselves here, but just like I said a minute ago, if I had 2 1/3, you can convert that, maybe you know how, into 7/3. We'll talk about that when we get the fractions. So if I asked you if 2 1/3 is rational, well, it may not look like it right there, right? But if you convert it, which we'll talk about another day, to 7/3, well, 7/3 is P over Q, and P and Q, the two numbers, are integers. 7 is an integer, 3 is an integer. So yes, 2 1/3 is rational, and so is 7/3. They're the same number. All right? What is not rational? Well, what if I put the number pi down? And I said, is pi rational? And you said, well, yeah, man, because pi over 1. You said it just had to be written as a fraction, right? If you write it as a fraction, it's rational. But that's not true. I didn't just say write it as a fraction and it's rational. I said write it as a fraction, and the numbers you use to make the fraction have to be integers. Well, 1 is an integer. What is an integer? Just again, it's a positive or negative whole number. 1 is an integer, but is pi an integer? Is that a whole number? No. So saying pi over 1, that does make it P over Q, but it doesn't fit the second part. The two numbers you use to make the fraction are not integers. So pi is not an integer. There's another number called e. You may not be familiar with this yet. If you go far enough along, you will. But the same argument applies here. If you say, well, e over 1, that's a fraction. E is just a number, guys. It's just like 2.79, blah, blah, blah. If you could say, well, I make it e over 1. That's a fraction. It is a fraction. But is it rational? No, because e is just some junky number. It's not an integer. So the fraction that you made did not contain integers. I know it's a little confusing, okay? So take a deep breath. We'll still do a few more examples. The rational numbers are where the bulk of the time is going to be spent here. The natural numbers, the whole numbers, the integers, those are just definitions, okay? So let's keep going. Let's clear this and keep going. I gotta find a better way to do this, or I'm gonna be going through a lot of paper. All right. So I'll write it up here again. Rational numbers are P over Q, where P and Q are integers. That's and, not plus. Again, same definition I wrote down on the other page. So we said normal fractions are rational, right? Like 2/3, that's a normal fraction, that's rational. -7/3, that's rational. Negative numbers are integers, no problem. We even said mixed numbers, or mixed fractions, if you want to call them that, are rational, right? Because all of these can be written as normal fractions using positive or negative whole numbers, which is what this means. Write it as a fraction with positive or negative whole numbers, and it's rational. So what we can say is most normal, well, we can just say normal fractions. If it's a normal fraction, positive or negative, doesn't matter, then it's rational. All of these are normal fractions, they're all rational. What about regular numbers? Well, regular numbers, you can put them over 1, can't you? 3 over 1, and that's a regular fraction. What if I took the number -19? Can't I write that as -19 over 1? And isn't that a normal fraction? So all of this is rational, all right? What's not rational, or what's less clear if it's rational or not, are the decimals, all right? So that's where the issue comes in, and I'm gonna make this easy on you guys because we haven't talked about decimals yet. I don't really expect you to be able to convert between fractions and decimals, so I'm gonna make this easy for you. 2 things to know if a decimal is rational. 1, it will repeat, or, and this is key, it's or, it's not and, it's or, one or the other. 2, it will end or terminate. Okay? If the decimal repeats, or if it terminates or ends, then it's rational. Because, I mean, the long and short of it is, if it does these 2 things, you can turn it into a fraction. I am not asking you to do that, so don't worry about it. I am not asking you to take decimals and turn them into fractions. You're not gonna have to do that in the homework. I'm just telling you that is the reason this is. Because if a decimal repeats, you can write it as a fraction. If a decimal ends, you can write it as a fraction. So, just for a quick example, let's say we had 1.378. Is that rational? Well, yes, it is, because it ends. 1.378, it ended, done. What if I said negative 0.3 repeating, right? Negative 0.3 repeating, which is the same thing as negative 0.33333, and so on. Is that rational? Well, yes, it is, because it repeats. It doesn't end, but it did repeat. So yeah, it's rational. So what kind of things would not be rational? Or what kind of decimals don't end and don't repeat? Well, think about it. We already talked about one here just a second ago, didn't we? Didn't we just say pi is not rational? And I gave a different answer that time. I said it's not rational because when I try to write it as a fraction, that doesn't fit the bill. Yes, that's p over q, but those numbers themselves are not integers, so it didn't work. Well, here's another reason pi is not a fraction, or pi is not rational, excuse me. What is pi as a decimal? 3.14, and I mean, I haven't memorized this, y'all, but you know, just blah, 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 right? It doesn't end, it doesn't repeat, it doesn't repeat, it does not end, so pi is not rational. Am I making sense? Okay, so let's review real quick. How do you know if a fraction is rational? Any normal fraction is rational. If it's positive or negative, if it's a normal fraction, mixed number, improper, doesn't matter, they're all rational. If it's a regular number, 3 or negative 19 or a million, it's rational because you can write it as a normal fraction. The decimals, the easiest way to do this is just to memorize this. I don't say that very often, but I will say it here. The easiest way to know if its decimal is rational is, does it repeat or does it end? And if you say, well, isn't that everything? Think about pi. Pi does not repeat, pi does not end, pi is not rational. One other thing I will mention real quick. There's another type of number that does not repeat or does not end, right? We said pi is 3.14295.7. Again, I'm just making this up. I really don't know. So not rational, right? Because it didn't end. It didn't repeat. Square roots of numbers that are not clean have the same issue. The square root of 5, if you put it in your calculator, think about it. What's the square root of 4? It's 2, right? What's the square root of 9? It's 3. So this will be somewhere between 2 and 3. But if you put this in your calculator, and again, I'm just making the number up, I don't have it memorized, you're going to see that it just repeats, or excuse me, it just keeps going. It never stops. Your calculator will stop it because your calculator runs out of room, but the decimal does not stop. And this is true of any number that's a square root that's not a clean answer, right? So this one, again, would still be somewhere between 2 and 3. But this one's going to be further up the line. And I'm, again, totally making this number up, but I'm just making the point here that square roots of numbers that you don't know, well, I shouldn't say that you don't know, but square roots that are not clean answers, whether you know them or not, doesn't matter, but square roots that are not clean answers are not rational. Decimals that don't end and don't repeat are not rational. So these are called irrational. All right? Irrational numbers. These are the numbers that do not fall in the rational category. Most decimals are rational. Most fractions are rational. Every regular whole number or negative whole number is rational. 0 is rational. The only numbers that are not, the only ones that are irrational, are numbers that never end and never repeat. How would you know? It'll either be a number like pi, or it'll be one of these unclean square roots, okay? Hopefully that's making some sense. Let's try to bring this all together with a little bit of a visual here. And this, if you'd like to, you can Google this. Just Google the number sets. This visual that I'm about to draw should be widely available on the internet and probably going to look a lot better than what I draw. I do not have any artistic skills to speak of, and you're going to see that right now. So the easiest way to think about this, honestly, guys, is containment. So let's take the natural numbers here, and let's make a little box and call that's the natural numbers. Try to remember, as we go through here, try to quiz yourself. What are the natural numbers? They are positive only, and they are the counting numbers. 1, 2, 3, 4, and so on, all the way out to infinity, but no decimals, no fractions, nothing like that. What was the next set? Do you remember? It was the whole numbers, right? And now notice what I'm going to do. I'm going to draw the box of the whole numbers, and I'm going to draw the natural numbers inside of it. Because think about what the natural numbers were. 1, 2, 3, and so forth. Aren't all those whole numbers? What are the whole numbers? Well, whole numbers are damn near the same thing, except they have 0. So think about what I'm saying here, because this is important. Wouldn't you agree that the whole numbers contain all of the natural numbers and then something extra? In this case, just one number extra, but a lot of times it's more than just one number. So this idea of containment is very important. All of the numbers in the whole numbers are natural, but then it also has 0. So the natural numbers are inside of the whole numbers. Think about what I'm saying here. It is important. The next set we said was what? The integers, right? We're going to scratch that out so that doesn't mess up our image here. The next one was the integers. And what were the integers again? The integers were what? Positive numbers, whole numbers, except we also had the negatives. So we put the plus minus here to remind ourselves. These are where the signs are. And again, the whole numbers are inside of the integers. The natural numbers are inside of the integers, okay? Then our next box, and that's why I scribbled this stuff out because this is going to get a little bit bigger. Our next box is the rational numbers. And again, what did the rational numbers bring to the table? They brought in most, fractions, and decimals. Not all of them. Don't forget about that. Not all of them. There is a small set, we'll draw them down here. There is a small set called the irrationals. And this is stuff like pi, square root of 2, and things like that. Okay, again, we're just recapping. These are not included with the others. The regular numbers do not fall in with the irrational numbers. The irrational numbers are out here off by themselves. And then there is one more number set that contains everything, and we call that the real numbers. Okay? So, 5 number sets you need to know. Wait, am I getting that right? 1, 2, 3, 4, 5, 6. You got the natural, which are inside of the whole, which are inside of the integers, which are inside of the rational. These are all inside of one another in this order. Smallest, next smallest, and so forth. Then there's a break, and over here we have the irrationals. They are not part of the other ones. And then everything is real. Okay? Again, there's much better diagrams than this on the internet. I just wanted to show you kind of how they're drawn, where they're coming from, things like that, okay? So let's wrap this up and let me show you a couple test questions, things that I might ask on an exam, things that'll be in the homework, stuff like that. What kind of questions can you expect to see with this kind of stuff? I may have to end up getting an erasable board here because this is just, I am just tearing through paper. Okay, so what might I ask you on the test? Something like this. I might say, what is the, and this is key, the word smallest set -7 belongs to? So I'm not necessarily just going to say, what's the definition of the integers? What's the definition of the rationals, etc. I mean, you know, that's obviously always an option, but I expect you're going to have the definitions. My desire is that you understand how to apply them and how to use them. So when we're talking about a number, let's say -7, think about all the number sets that belongs to. Is it a natural number? Is it a whole number? Is it an integer? Is it rational? Is it irrational? Is it real? Well, let's think about this. Is this a natural number? Natural numbers are whole positive numbers, so no. Is this a whole number? No, because whole numbers are the same as the natural numbers, they just have 0. Is this an integer? Yes, because integers are the first time that we see positive and negative signs together. Yes, this is an integer. Now that keep going. Is it rational? Yes, for 2 reasons. 1, because I can write it as a normal fraction, right? That makes it a rational number. And think about it. Where's that drawing I just had a second ago? Think about what we said in the drawing. Weren't all the integers inside of the rational numbers? Just by containment. If it's an integer, it's inside the rational numbers, right? Didn't we say that the integers are inside of the rational numbers? So when you start asking about a number like -7, and you say, is -7 rational? Well, you said it's an integer, and the integers are inside of the rationals. So think about that kind of containment, right? It is an integer. All the integers are in the rational numbers. So by that definition, it is rational as well. So you can use the containment argument. The integers are inside of the rationals. That's an integer. So therefore, it is also rational. If it's rational, it cannot be irrational. So that's out. And is it real? Well, yeah, every number that we're going to talk about in this course is real. So what is the smallest set that it belongs to? The real numbers are the largest set. The rational numbers are the next largest set. The smallest set that this belongs to is the integers. The first set that -7 you find it in is the integers. You don't find it in the natural numbers because it's negative. You don't find it in the whole numbers because it's negative. You find it in the integers because that's where the negatives are. Hopefully that makes some sense, guys. Let me show you one more and give you an idea. Let's say I gave you, and again, a lot of this is going to focus on rational because that's where the issues are. Let's say I gave you a list of numbers here. Let's say -3.75. And then we'll say 11, and then 0, and then we'll say -9/4 pi, and then let's do one more. Let's say positive. We'll do positive this time. 4.7 repeating. All right. So you got 1, 2, 3, 4, 5, 6 different numbers. All right. And the question is, which ones are rational? So go through and think about each one. Is that rational? Why? Is that rational? Why? This one, this one, this one, this one. Are they rational? Why? Let's throw one more on there, actually. Let's do root 13, square root 13. -3.75. Is that a rational number? Yes. Now think about why. There's 2 reasons. One maybe less or more. Well, there's only one reason, but you can get there 2 different ways. For one, I told you, any decimal that stops or terminates 3.75, negative, positive, doesn't matter. 3.75, it ended, so it's rational, just simply by that argument. It's also rational, and again, this part may be more than you're comfortable with right now, because you can write it as a fraction. That also makes it rational. But again, I'm not asking you to do that. So this one's rational because it's a decimal that ended. And we said if they end or repeat, they are rational. What about the number 11? Is it rational? Well, yeah, but why? 2 reasons here. You could write it as a regular fraction, 11/1. That makes it rational. Also, isn't 11 a natural number? And aren't the natural numbers inside of the whole numbers, inside of the integers, inside of the rational numbers? Think about the boxes again. So if it's a natural number, which it is, then it's a rational number by default. So you can also say that. I think the fraction argument is probably the easiest way to go, though. What about 0? Is that rational? Well, yeah, because whole numbers are inside of the rational numbers. But again, I think the fraction argument is the easiest argument to make because 0/1 is a normal fraction. Be careful. 0/1 is an okay fraction. 1/0, that is not okay. That's a different story altogether. -9/4, is that rational? Well, yeah, because it's a regular fraction. So yeah, it's rational. So is 0. That's just a normal fraction. Positive, negative, doesn't matter. Pi. Well, you know pi is not rational because I told you it's not. But why not? Because again, if you wrote out the decimal, whatever it is, I don't know, it never ends, it never repeats, it never stops. If a decimal doesn't stop, if a decimal doesn't repeat, then it is not rational. What about 4.7 repeating? And just like 3.75 or -3.75, this argument is very much definition. I told you already, if a decimal repeats, it is rational. Nothing else to say there. The last one is also definition. I also said that any square root of a number that's not clean, because you know the square root of 9, that's 3, and you know the square root of 16, that's 4. But 13 is somewhere in between. This number, if you put it in your calculator, which you shouldn't be using in this class, should have said that, you will know, I mean, I don't know exactly what the number is, but it's going to be like 3.7924, whatever. It's going to go on forever. It's never going to stop. It's never going to repeat. So if it doesn't stop and it doesn't repeat, it's not rational, okay? So these were rational because this one stopped, this one repeated. This is rational because it's a normal fraction. And these two are rational because they're just regular whole numbers, 0 and 11. Numbers like pi and numbers like unclean square roots like 13 are not rational. And now we'll wrap it up for the first video, guys. Congratulations, you made it through. We're done with video 1. Like I said, feel free to send me any kind of feedback. I mean, telling me just make it better doesn't help. I can only make it so clear. This camera just does not seem to want to focus any more than this. So if it's a little grainy or weird, for the moment, I don't know what to do about that. I'm looking into it, though. Hopefully, we'll be able to get something going. I am going to probably switch to an erasable board because I just went through like 20 sheets of paper. This is crazy. But anyway, any thoughts or ideas, feel free to share them. I don't use Zoom conferencing just simply because I don't have a board big enough to do a lecture on, guys. If you were wondering why I'm choosing to do pre-recorded videos, that is why. Just simply, can't go on campus right now, so I can't use the classrooms and the board. I have no board in my home. So this is what we're doing for now. Hopefully it makes sense. Rewind it, slow it down, pause it, take your time, and let me know if I can help. I'll see you guys in the next video.